Well, hello again. This is Dr. Richard, and I'm going to be your host as we go through Physics 2, in which we'll detail electricity and magnetism and optics. We're going to start with electrostatics. And electrostatics just is going to deal with charges that don't move. And then we're going to talk about all the shocking revelations that this is going to entail. And that's proof that it's never too early in the semester for a horrible physics pun. But if you'll forgive me this, let's just move on. So, big ideas. Just like in class, here are the big ideas for this video lecture. So if it's important, if you are wondering, will this be on the test? Oh, will properties of charge be on the test? How about conductors and insulators? Charging objects? The answer is yes, which is why I point them out in these big ideas. So if you're in class and I see these on the board, or you see these on the board, it's probably important. And that was just a reminder. So let's dive into the material now. So first, where does this electricity and magnetism fit in with physics? Well, there are four things we call fundamental forces. First is gravity. You deal with this. This is, Newton had his little apple, it fell. Electric, or electroweak, these are charges. So this would be a plus charge and a minus charge, and they attract and repel, which you've had some experience with. Weak nuclear force, this keeps, you've got your little proton in the middle, you've got your electron buzzing around here. Electroweak keeps this electron, right here, from flying into the nucleus. And then strong nuclear, in the nucleus you have a bunch of protons. And these will try to repel each other, so the strong nuclear holds them all together. So in this case, your strongest force is down here, your weakest is up here. So strongest goes down here. However, at the top, gravity, the reason you see gravitational forces is that they act over a longer range, and the strong nuclear acts over short range, because the nucleus is pretty tiny. So what we're trying to figure out is how this electric force works in. And a lot of work was done in the late 1700s and early 1800s. But first, let's go through history. So you have the Greeks. This guy is Greek, and he took a little rod and rubbed it on a piece of amber. Amber, if you've ever seen Jurassic Park, actually let's do an homage to Jurassic Park. We'll put a little mosquito in here. And since he's not going to do gene editing, he is going to take this stick and rub it on this piece of amber. And then he found out that if he touched this little stick to things, little pieces, it would attract them. And this was a lot of fun. In fact, the word amber in Greek is electron, which hopefully this word looks familiar to those of you today. Fast forward to the 1700s. Now we have this guy, Ben Franklin. You may know him because he flew a kite, and then the kite got, I should have made the kite red, and the lightning yellow, but that's all right. Got hit by lightning. This is not entirely true. What he did have was a kite filled with little horsehairs, and he noticed that the horsehairs were standing on end. This is like before an electric storm. Your little arm hairs will stand on end. And he thought this was pretty neat. So he did a lot of experiments with this to figure out, well, what was going on. Now, we've all got some experience with this. It's a cold day, and let's say you've got an adult, or sibling, roommate, whoever, and you've got an idea. So you walk across this carpet in your socks, and you go, and you go, doo-doo, 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 and you shock them with lightning from your hand. Well, that's exactly like the piece of amber, except it's a little more satisfying, we'll put it that way. But let's look at some other examples. Now let's talk about this demo. So in this demo, you rub this rod right here on something, piece of wool, and then you touch this metal ball, and then you'll notice that these two little pieces of foil start to repel each other. All right, this little device is called an electroscope, and you want to ask why this happens. Well, something was flowing, and this is kind of what Ben Franklin thought. Now, granted, Ben Franklin, when he did this, he said they were plus charges. He got it wrong. He didn't realize electrons moved. We're going to come back to this later, but for convention's sake, it's It's weird. But that's okay. So then, this charge flows down here, and you get a whole bunch of negatives, and they repel. But he noticed that when you rub a glass rod on, like a piece of linen or something, it would go the other way. So rubber rod on wool makes it go one way. You touch it a different, it goes the other way. Huh. They concluded something had to be flowing. Now another demo, and the only requirement for this demo is that you have to have more hair on your head than me. So you rub the balloon on your head. And then you stick it to this wall. And it'll stick. Which is really weird. You should try this right now. If you have a balloon, if you don't, go buy one. Or borrow one. Or if your roommate takes clowning classes, borrow one of theirs. And you can stick to a wall. And we're going to come back to why this happened. But the whole goal is that something had to move. So negative charges moved from your head. Which means what was left on your head are now all these positive charges. So you've charged the balloon and your head, except the balloon's lighter weight, so it can stick to the wall, where your head won't. We're going to come back to this in a little bit and kind of delve into it. But right now we're getting the idea that charges flow. Alright, so let's talk about some general properties that you should know. The first thing is that when we talk about things in this class, it's electrons that are going to be moving. Protons are more massive. What does more massive mean? It means they have more, only word that rhymes with sminertia in the English language, inertia. Yeah, they have more inertia. So they like to stick where they are. All right, they resist accelerations better. So generally electrons move. Protons don't move as much, or at least not a noticeable amount in terms of this class. Next, electric charge is conserved. This is to say that it's not created or destroyed. Not created or destroyed. So whatever charge you have, all it's going to do is move around from one point to another. The third thing we're going to talk about is that electric charge is quantized. That means it only comes in increments of n times this fundamental electric charge. This was done by Millikan in 1909. He dropped little bit of oil, and watched it move. It goes up, it goes down, falls for mg. He balanced that with an electric force. And he just watched those drops of oil and found out that, hey, look, based on how they move, charge must be quantized. And the final thing you need to know is the SI unit of charge is the coulomb, or coulomb, named after Charles Coulomb, who we're going to talk about in a little bit. It is a very, very small number. And that's because coulombs are gigantic. If you had 1 coulomb of charge 1 meter apart, it would be the force of a battleship, like the weight of a battleship. That's a lot. So this number is really big. So now that we've got a couple of the properties, what I want you to do is pause the video. Okay, please restart the video if you paused it because you need to hear what I'm going to say next. Okay, I would like you to make a list of what are some properties of good and bad thermal conductors. What do they look like? What do they, smell like is a little odd, but what do they look like? What do they do? What types of materials are they? And what are some properties of good and bad electrical conductors? So what heats up really fast? What gives off its heat really quick? What's a good thermal insulator? What's a good electrical conductor? What do they look like? Pause the video, write a couple lists, and then compare and contrast your list. Okay, now that you're back, let's go to the next slide. Hopefully what you've noticed is that a lot of these things look the same. Things like metals, shiny, all of these things, which is also a way of saying that good thermal conductors are generally good electrical conductors. I'm going to put generally. For the most part, they are. What this tells us is that the electrons actually play a part in thermal conductivity. They're mobile, they can move around in the crystal lattice, or the structure of a metal, and they can do that, which is really cool. I think it's cool, but I'm a physicist, so whatever. If you think it's cool, you might be a physicist too. So then what we do is we figure out, well, how well does it conduct? So if it is a bad conductor, it is an insulator. So all insulator means is it a bad conductor, and we'll say that the electrons are held tightly. Now let's cross that T. The electrons are held tight, as opposed to a conductor where the electrons are only loosely bound. That means they can flow and run around places. It means you can run a current through them, which we'll get to later. Semiconductors in between, there are some properties that it can do. And then eventually we'll get to superconductors, which have no resistance to charge flow. And we'll talk about that later. That's enough to get its own little section, and it's fantastic. All right. So I said we'd revisit the last two charging demos that we would do, and here we are. The two charging processes. We talked about how charge is conserved. Remember, charge is conserved. So what we're looking at, if you know that charge is conserved, you have to take the electrons from this rod and then put them here. All right? So in order to conduct things, you have to transfer charge from one object to another. How is this different than the balloon? Now before we go on, what I want you to do, I would like you to take your piece of paper. I would like you to draw this little scenario, and then I'd like you to sketch a hypothesis. Just where's the charge on these things? So take a moment and do that. If you've got a roommate, share with them, ask them how this would work. If you have a balloon and your roommate's not in physics class, ask them to rub the balloon on their head and stick it to the wall, and then see how long it sticks. My record's 3 hours. Now we know that this balloon has charge, because you transferred charge to the balloon by rubbing it on your head, which means it was transferred by conduction. Good. Now it's safe to say that Westerman Hall does not have electric walls. You can touch one, and it won't be electric. However, if the wall's not charged, it must be neutral, which has the same number of plus and minuses. Well, what do minus charges do? Minus repels minus, which means the wall's negative charge goes over here, which means the positive charge in the wall is close to this negative charge. They attract, and now you have a balloon that sticks to a wall. Eventually the air will bleed off this charge and the balloon will fall, but it's a pretty neat demo. And they call this induction, which just means that the charge in the wall shifted. I hope this has been helpful, and next video we're going to talk about Coulomb's law. Have a good one.